How's it make you feel?
Great.
All right, let's take a look at page 254. We are going to continue practicing our graphical connections between f prime, and then the second derivative. Today we're going to take a look at a graph assuming that it's a first derivative graph. Now yesterday we did kind of a helpful chart and an example, so if you do want to get that out and reference it, you can. You will not have that chart though for the quiz or the test. Okay, so it's a helpful tool, but you got to be familiar with it for later. What we're going to try to do is, if we assume that this is a derivative graph, we're going to try to write down as many things as we can about the original function, but also the second derivative. And when I went through this, I'll just give us some helpful hints. I was able to come up with 8 things about the original function and 5 for the second derivative. I want to see if we can get there. Okay? So can we think about, maybe before we actually tackle these conclusions, can we list what the different characteristics of this graph represent? What do the points mean on this graph? Yeah, Griffin?
The max min values.
Max min value for f of x? Or
I thought we were talking about for on like f prime of x.
This would be f prime. Okay, so the points represent f prime. If this is the graph of f prime, that's what the points mean. So this is a slope of 5. This is a slope of -2. Okay, that's what the points mean. What would the slope of this graph represent? The slope of the first derivative. Good, Anush? That's the second derivative. What would the concavity of this graph represent? Now we're looking for a type of function, yeah?
Wouldn't that be like where L prime of x is increasing?
Yes. Okay, so if the second derivative is increasing or decreasing, that's telling us something about the third derivative. Okay? Now, we are not going up to the third derivative. So notice how we probably are not going to have to analyze the concavity of this graph to help us with any conclusion. Okay? So the points mean what the function is. The slope is the next derivative. The concavity is the next derivative after that. Okay? I hope this makes sense because let's assume the graph was f of x. The points would represent f of x. The slope would represent the first derivative. And the concavity represents the second derivative. Right? We're just doing the same connection, but applied to a different graph. So everything just moves up a derivative, if you will. Okay, so let's see what we can figure out about f. We have 8 things that we want to try to discover or pinpoint. Where do we want to start? Quitting is not an option. What do you think, Christian?
Where f of x slope is positive or increasing or decreasing.
Okay, so f of x increases on what interval? Or vols. It might be 2. Yeah?
-2 to 1, and then 3 to infinity.
Because?
Because this first derivative is positive there.
First derivative is positive. Okay, so since this is the graph of the first derivative, all of our justifications should say because f prime does something, because f prime is something. So they should all be because f prime. I like it. 7 more to go. Can we do a similar one? F of x decreases on
Continue talking.
Stay in the interval, Steve. It's the other intervals don't need Steve's not the
Opposite.
I don't think there's one.
opposite of those. Okay,
Negative infinity.
negative infinity, -2,
And 1 to 3.
1 to 3. Because the derivative is negative. All right? Yeah.
F of x is quartic.
F of x is quartic because
The derivative of f of x is cubic.
is cubic. Okay, because f prime is cubic. Looks good. Good, Megan?
There's like maxes and mins at -2, 1, and 3 because that's where
Okay, so f of x max at, and then we'll do f of x min at. So can we distinguish between the two of them? Keep going, Christian? Yeah?
You have a minimum at -2 because the slope goes from negative to positive.
Okay.
The same thing happens at 3 for the same reason. And then at 1, you have, what did I say the first time? Okay, at 1 you have a max because the slope goes from positive to negative.
Okay, so minimum, we'll say f prime goes negative to positive. Okay, so f of x is changing, decreasing to increasing, creating that minimum. And then for x equals 1, because f prime changes or goes positive to negative. All right, we got 3 more. What do you think, Anuj?
Does n behavior count as one?
I didn't list it, but what would you say for end behavior?
As f of x like goes off to infinity,
Mm-hmm.
or as f of x approaches infinity,
Yeah.
I guess. What am I trying to say? It goes up and to the right and down and to the left. I mean, not really sure.
Actually, it would go up to the right and up to the left.
Oh, that's true.
What's tricky is notice how on the left-hand side the first derivative is negative, so you're decreasing from the left. That means if you go to the left, you'd be going up. That's what's a little tricky. But I didn't count that as some of the 8. Yeah?
It's concave up.
Ooh, good. Notice how we didn't mention anything about concavity here, okay? So the slope of this graph is telling us something about the second derivative, and we should know the connection about the second derivative to the original. So let's see if we can analyze the slope of this graph to help us with concavity. Griffin, where'd you want to go? F of x.
It's concave up on negative infinity to 1, and then 2 to infinity, because that's where f prime of x is increasing.
Because f prime of x is increasing. Okay, the slope is going up. So if the slope of this graph is positive, we know the second derivative would therefore be positive, and that means the original function would be concave up. I like it. Can we write a similar statement? Notice how 8 seems like a lot, but as soon as you find 1, like the other ones kind of fall into place. So f of x is concave down. Where would that be? Go ahead, Cole.
1 to 2.
Because, good.
F prime of x is decreasing.
f prime of x is decreasing. Perfect. All right. That's 7. We got one more. Go ahead, Megan.
Are the maxes and mins like points of inflection?
Yep. Okay, so f of x has inflection points. Notice how you already said where f of x is concave up and concave down. So if you're changing concavity, you must have inflection points somewhere. So if we look at our intervals, we go from, this should be -1. We change at -1, and we change at 2, because the first derivative has a max slash min. You guys went through that easier than I thought you would. Probably easier than you thought you would. You said 8 and you were like, oh no. All right, let's try 5. So what are some conclusions that we can make about the second derivative? Okay, if we look at our little list here at the top, the second derivative information or values are going to come from the slope of this graph. Let's see if we can try to find 5 things. Can we figure out where the second derivative is positive? Where the second derivative graph would be above the x-axis? Yeah?
Negative infinity and -1.
Yeah?
And 2
Because
f prime of x is increasing.
f prime of x is increasing. All right, we'll do a similar one. The second derivative is negative on -1 to 2 because the first derivative is decreasing. Let's see, we said where the second derivative is positive, where the second derivative is negative. Can we say where the second derivative is 0? What are you thinking, Nish?
-1 and 2.
Because?
F prime of x has max or min.
Has max or min. Good. We'd also have to be careful about a level spot. That would be another point to look out for, but we don't really have that here. All right, we need 2 more. Actually, 1 more. This last one we did took into account 2 of them I had on my paper, so that's fine. We have 1 more. You see it, Christian?
Quadratic.
The second derivative is quadratic because the first derivative is cubic. Nice. All right, so the video assignment was assuming that this graph was the original function, and then we went through our different conclusions. We just did if this graph was the first derivative, so then we went through our different conclusions. All right, we're going to switch the page. We're going to take a look at another graph. And we're going to assume that this one is the second derivative. So let's list what the points tell us, what the slope tells us, and what the concavity tells us. The points tell us f double prime. The slope tells us f triple prime. The concavity tells us quadruple prime, or we'll do like x to the fourth in there. Now, we're not going any higher than 2. So we should not have to analyze the slope of this graph, and we should not have to analyze the concavity of this graph. It looks like we're only looking at points. Okay, so what can we conclude about f? Based on my paper, I have 4 here and 7 here. The points on this graph represent the second derivative, so think about how the second derivative is related to the original function.
Can we start on the first derivative first and like work our way down?
You want to do that? Yeah, we can go backwards. Okay. We can bounce back and forth. I don't care.
F prime is increasing on the
Mm-hmm.
interval 0 to 3 and 3 to 3.
Perfect. Because
Because on the graph F double prime is positive.
it is positive. Good.
How they discuss it.
I
I'm gonna
know.
say it right in front of you.
I feel like I need to put like high-powered microphones in front of.
I really want to hear all that conversation.
I just feel like
Dude he doesn't even deserve the 1 point that we get. He doesn't even deserve that.
They're brutal.
Let's say Eddie.
Let's see. F prime is decreasing negative infinity to 0. I think that's it.
Yeah.
Because second derivative is negative. If we're changing increasing to decreasing, we're creating something. Yeah?
Max or min
Max or min?
on x equals 0 and x equals 3 because in, wait. 3 is not a max or min, but it, wait. I just think of what it's called. I know, wait.
Alright, we're waiting.
All right. Well, let's do 0. Let's do 0 first. If we're negative before, positive after.
That is minimal.
All right. Min at x equals 0 because second derivative changes negative to positive. What about 3? Is it a max? No, because we'd have to change positive to negative, and that doesn't happen. So what are we at? What is the first derivative at 3? Level at x equals 3 because first derivative equals 0, but doesn't change sign. Bless you.
oh.
1, 2, 3, 4. All right. So I had 7, but some of these took into account other ones. So now we have one more.
Sounds good.
One more. Yep. Yeah.
Quartic.
Quartic. All right. F prime is quartic because F double prime is cubic. Good. All right. Let's try F. let's see, over here we said the second derivative is positive on these intervals. So that means the first derivative is increasing. But if the second derivative is positive, what does that tell us about f of x? Concave, positive, up, okay? So f of x is concave up on actually the same intervals because second derivative is positive. Similarly, f of x is concave down on negative infinity to 0 because second derivative is negative. All right. If we identified concave up and concave down intervals, that must mean we have some points of inflection because we're going to change somewhere. So f of x has point of inflections at, if you look at the intervals, where do we change concavity? On this graph, we change there. Look at your intervals. So we're concave up here, and we're concave down here. We change concave up to concave down or vice versa at 0, but not at 3, because 3 wasn't found in here. So we really only have one point of inflection. Now, our justification should be because f prime or f double prime does something. What's special about this spot at 0 on the f double prime graph? Changes sign. Now, since it changes negative to positive, you know f of x is changing concave down to concave up, which is a change in concavity nonetheless. Okay, so it's a point of inflection. All right, one more. F of x is quintic because the second derivative is cubic. Are we starting to get a little more comfortable?
Yeah.
Better? I hope. Okay? Because we spent some time on it. Every day is a little bit more. We'll get there eventually. Okay. What I want to make sure we do today is take a look at some calculator active questions because on the AP exam you will be able to use a calculator on certain sections, and graphing a picture on your calculator or using your calculator can make your life go so much quicker and faster because it's a timed test. So I want to go over some strategies that you can use when you have a calculator handy. Don't feel obligated to do everything in your head or on your paper because you have this as a tool to use to your advantage. Okay, so take a look at the next one. If the function f prime is cosine of natural log of x, okay, that's the first derivative, of a twice differentiable function. Do you know what that means? Twice differentiable? Yeah?
That function is able to be, like the derivative, the second derivative exists in that function.
There you go. Second derivative exists. Okay, so you actually have an original function, but also a derivative function that doesn't have any holes, any jumps, any asymptotes, no endpoints, no sharp points, and no vertical tangents. Okay, so you know those characteristics hold 2 times. So what I recommend doing is if you have a calculator and they give you an equation, graph it. You might not always have to use the graph, but at least it's going to be quick and you have it available if you need it. So on your calculator, go to y equals, and we'll type in cosine natural log x, and if you have 2 open parentheses, make sure you do 2 closed parentheses. Since this is a trig function, make sure you're in radian mode. All right. Now, if you look at part A, it says on the interval from 0 to 10. So in your window, let's go from 0 to 10 for the x's. You can choose to count by whatever you want, and they don't really give us any information for y values, so you can make those whatever you want, but we can always go back and change them if we have to. Let's go ahead and hit graph just to see a picture. All right, we have a lot of empty space, right? So let's go back to window, and instead of going -10 to +10 for the y's, maybe we'll do -5 and 5. We'll chop it down a little bit. Good. Okay, we still have some empty space there, so if you want to keep going further, you could. -2, +2. Okay, looks pretty good. So this is a first derivative graph. We have to keep that in mind, okay, f prime. So looking at part A, find the values where f of x, okay, the original function, has a maximum. Can we use this picture to help us find that location? Can we describe where we should be looking? Go to Noosh.
Looking for a 0 that changes from positive to negative.
Okay, so if you look at the graph, it looks like we have two x-intercepts. One's at the very beginning, and then we have the other one kind of further in. So if we want a maximum, we want the first derivative to change positive to negative. Okay, that's our justification we're actually going to use. So it looks like that happens here. Now, since we're using our calculator, we should be able to figure out that point exactly, okay, at least to 4 decimal places. Are we familiar with how to find an x-intercept on our calculator? Some of you might, some of you might not. Okay, we're going to hit the second button and then hit trace. This is going to bring up the calculate menu where you can do maxes, mins, values, intersection points. You can actually do derivative graphs, and we'll talk about integrals later this year. But number 2 is 0. So I want you to select number 2. And it's going to ask you a few questions. I want you to move the cursor to the x-intercept that you want to find. And you first have to pick a left bound. So hit the left arrow a few times and then hit enter. You should see an arrow pop up on your screen. That's completely okay. The next question is a right bound. So you're going to have to go to the right of where the x-intercept is. Doesn't really matter where as long as it's to the right, and then hit enter again. So what you're doing is you're telling your calculator that the x-intercept you want it to find is somewhere between those two arrows. So the last thing is a guess. We're going to move the cursor to where we think it is and just hit enter. So when that word 0 pops up, you should have the exact number that you want. All right, so we'll say x equals 4.810. Okay, you go to 4 decimal places. You could either write 4 if you chop it, or you can round it to 5. Up to you. So 4 or 5 there is perfectly acceptable. Okay, so this is a max on f of x because f prime changes negative to positive. Do you think we can do B? It's basically the same question, but looking for a minimum. Oh wait, this should be positive to negative. My bad. Negative to positive is for the minimum. All right, so let's try to find a spot that changes negative to positive. That looks like very close to the y-axis at the very beginning. So we're going to repeat the buttons. Okay, second trace, select number 2. we're going to move the cursor to where we think the x-intercept is. We got to hit left a few times and hit enter. Go to the right a few times and hit enter. Go back to where you think it is and hit enter. All right, 0.207. You can chop it at 8 or you can round it to 9. Are we doing okay with the calculator? Yeah? Especially you. It's going to be a learning process. All right. Take a look at part C. On the interval from 0 to 10, at which x values does the original function have a point of inflection? If this is the graph of a derivative, where should we be looking? Maxes and mins. Okay, so on the graph, it looks like we have a maximum clearly at the top right there, and no minimum the rest of the way. Okay, so we're going to have to find that high point. So on our calculator, we're going to let it do it for us. We're going to hit second trace, and we want to find a max, so we're going to select number 4. We're going to move the cursor to where we think the maximum is. And it's very similar to how you select x-intercepts. We're going to hit the left arrow a few times and hit enter. Hit the right arrow a few times, hit enter, and then go back to where you think the maximum is. Now if we round or chop that to 4 decimal places, we're basically 1. So x equals 1 is a point of inflection on f of x because first derivative has a max in this case. So far, so good. All right, so that was kind of a free response type question where you actually had to do the calculation and the finding. We can definitely use calculators to help us on multiple choice type problems. So let's check out the next one. On the interval from 0 to 10, it's the same interval. How many minimums does the graph of g have if they give us the derivative equation? Okay, calculator active still. So I highly suggest, if you have a calculator, graphing the function they give you just in case you have to use it. So let's type in sine of x, and then we'll divide. Make sure you put x plus 2 in parentheses because you're dividing both of those terms. We already know our window is set from 0 to 10, so we'll just go ahead and hit graph. So if this is the graph of a derivative, where should we be looking to find a minimum? Yeah?
Negative to positive x-intercepts.
Negative to positive x-intercepts. Okay, so let's see. We have an x-intercept. Looks like at the origin a little bit. There's another one there, and kind of another one here. I saw it dip down a little bit at the end. But negative to positive seems to only fit this description on the graph. So if that's the only spot that we have, okay, how many is the question it's asking? Looks like we only have 1. Maybe we'll say, just so you have this in your notes, graphed on calculator and looked for negative to positive change. All right. we'll stop there for today. On Monday, we're going to take a look at a few more kind of multiple choice type questions that are not calculator active. So these ones we might have to think about a little bit further. But I'm getting the vibe that we're doing a little bit better with these relationships. I hope so.